our product line that we use for commercial refrigeration, this AK, it's on the front of every part number we have. It stands for Adapt Cool. That's the name of our product line. And then you have the hyphen, and then PC stands for pack controller. So some of our other products, the AKCM, that's a communication module. AKXM, that's an expansion module. So this kind of follows that. And we call this wonderful and amazing controller you can see on your screens now the PC 782 pack controller. I want to just briefly touch on how we use that to control a transcritical system. So we're going to look at the sensor abbreviations that are confusing for some, and then we'll touch on the main control areas. So this is kind of a basic overview of our medium temp transcritical system. Let's look at the sensor abbreviations. I get a few complaints about this, like they're confusing, but I think if you hear the logic, they make perfect sense. So first one we'll look at is the suction pressure. Most people are used to seeing that called SUCT-PSI. For us, the P represents a pressure transducer. The O represents outlet of the evaporator. So our line coming back from the cases, we want to know the pressure leaving the evaporator. So that's pressure outlet. Then we go up. S, the uppercase S means it's a temperature sensor, and it's on the suction line. Temperature sensor on the discharge line. Pressure transducer on the line to the condenser. S3C, I don't have a good answer for. It's an anomaly. S means temperature sensor. C, I'm guessing, means condenser. The 3 is a mystery to everyone. And we're not changing it. So there's that. Then we have a temperature sensor on the gas cooler outlet. A pressure transducer on the gas cooler outlet. Now we have a new one, the V for valve high pressure. A pressure for the receiver. And then the valve for the receiver. So the uppercase letter, and this is all through our software and various controllers, P represents a pressure transducer, then the descriptor. S represents a temperature sensor, then the descriptor, and then the same for the V for valve. Now that face that just went across is because I just discovered that PowerPoint has motion paths. I'm childish and I could not help myself. So in our mode 1, we're going to look at these. We're going to go through mode 1, which is just using the medium temp compressors. Then we'll talk about parallel compression. Then we'll talk about ejectors. So mode 1, we've got 4 basic control areas. We've got the suction groups we need to control. We need to control the fans on the gas cooler. Got to control the high pressure valve as well as the receiver valve. Those are our main components. Here's how we're dealing with return from the evaporators. Here's how we're dealing with the discharge heat of the compressors. Here's how we're getting liquid. And then the receiver valve is dealing with the gas in the flash tank by bringing it back to the medium temp. So we're just going to focus on the high side. So I've cut off any cases below or from cases. So again, these are controlled by our wonderful and amazing, powerful pack controller. So we're just going to take a caption of the 4 areas we identified. So coming into our medium temp suction, we've got return from the flash tank, where we're venting off the flash tank, as well as our suction line return from medium temp evaporators. The sensors that we need for that are going to be the evaporator outlet pressure. We've got a sensor on the suction line so we can monitor superheat, so we can do something if we realize we're getting liquid back. Then for alarming and compressor safety, we have a sensor on the discharge line as well as a pressure transducer on the line to the condenser. So those are all inputs. So we've used 4 inputs so far, all analog inputs. And then our devices are going to be our 2 compressors. So there's a couple of relay outputs that we're going to turn on and off. And then we'll have an analog output to send 0 to 10 volts to our inverter. So the set points for the suction group are going to be the TO set point. So that's our target temperature. It's something to note that this isn't the word to, like going to the store. This is actually an acronym like we saw on the sensor abbreviations. It's a new one. When you see the T, that means it's a pressure converted to a temperature. The reason that we do that is it's very common, maybe even on some of our legacy devices, that you put your set point in for your suction groups as a pressure. And so that causes you to need a PT chart everywhere you go, either in an app or in your pocket, to pull out and determine plus 20 means 44 pounds. 44 pounds is my set point. We simply do that lookup in the background for you. You just put in the temperature you want, and then we reference this transducer and convert that to a temperature. And then as far as staging compressors, we use what we call a neutral zone strategy. And basically the neutral zone are limits above and below the target set point to where before you bring stages on and off so that you don't chatter the compressors and short cycle the system. So our neutral zone diagram, the illustration kind of goes like this. We've got an example here. Set point is plus 20, so that's our reference. And then our neutral zone is set to 4 degrees. So again, the neutral zone is like a deadband. It straddles the set point. So, we've got our set point here, and then we're straddling it with the neutral zone. So if you reach half the neutral zone plus the set point, which we've done here at this point, we call that the plus zone. If you go to one of our controllers and you look at a detailed status and you see plus zone, it means we're more than half the neutral zone above our set point. And plus zone means we're going to turn on the next stage of capacity. The opposite side of that would be what we call the minus zone. So once we turn that compressor on, it's a little too much. We've ramped down the inverter. The pressure is still falling. We get to this point. We enter the minus zone. Now it's time to turn a stage off. And then it'll float back up. When you're not turning something on or off, that's when you're actually within the neutral zone, which means you're no more than 2 degrees higher or 2 degrees lower than the set point that you define. And when you're in the neutral zone, you use the VFD to maintain capacity. So you ramp that between 30 and 60 hertz to keep you at temperature. And then there's a little highlight to show that here we're just moving, no call for going up or staging down. So if you go to one of our controllers and you see plus zone or minus zone, that confuses some people, but plus means I've either just added or I'm about to add capacity, and it means I'm still above set point plus 2, or I'm still below set point minus 2 if you see minus zone, and that'll display until you get back up into the neutral zone, at which point it'll just say normal control. So that's our suction group control. The gas cooler fan control is actually really straightforward. So we've got our lines coming from our medium temp compressors, the discharge coming into the gas cooler, leaves the gas cooler and heads towards the flash tank, really heads towards the high pressure valve and into the flash tank. So the sensors involved are just 2. We've got S3C, which again, for unknown reasons, is the ambient probes called S3C. And then we've got our gas cooler outlet temperature. The gas cooler outlet temperature, I just want to point out from having done a few startups and finding these largely not installed correctly, needs to be within 3 feet of the exit of the gas cooler. You've got high temperatures. The lines typically aren't insulated. And if you put it 6, 8, 10 feet away from the outlet, the temperature changes drastically. So it needs to be really close to the outlet so that it's getting the best picture of conditions leaving the gas cooler. And then devices, we simply have either an inverter or a 0 to 10 volt signal going to ECM fan motors. Something to note on that signal, typically for transcritical systems, people invert that and they actually control from 10 to 0, where 10 means fans off, 0 means full 100% capacity, so that if you were to lose that connection for any reason or upon controller failure, your gas cooler fans will go ramp to wide open. So those are our sensors in our device. The control strategy is pretty basic. We call it minimum TM, minimum temperature difference, but it's really just a delta between the ambient temp, which is the air coming into the gas cooler, and then the gas cooler exiting temp. We use a floating reference mode so that basically, as the ambient rises and falls, our 5 degrees difference just rises and falls with it. It's very similar to what's been done on the past with TD control. And then a couple of the key set points here. We have a gas cooler maximum reference, which means it won't let you float above a certain percent if it gets too high. And then what some people refer to as fast recovery. Our version of fast recovery is our absolute max. And basically, if you hit that temperature at the outlet of the gas cooler, it forces the fans to 100%. Another feature of the absolute max setting, it can shut down compressors if it needs to. It'll do what needs to be done to regain the high side of the system. So basically, the pack controller ramps the fans up and down to maintain a difference. One other quick note on the temperature sensors, these get reversed pretty often. And what that causes is the ambient would be here reading a higher temp than what it thinks is the outlet down here. So, it basically never turns the fans on. It thinks that it would make the gas cooler think that it's cooler than it actually is. So if you're struggling at a startup or in the field to get fans to turn on, decent chance that those 2 sensors got reversed. So the high pressure valve, this is one of the two new components that we need. If you'll remember, to get from the high side of the system in supercritical fluid region down into the dome where we have liquid and we can change state and do work, we needed the high pressure valve. The way this controls is kind of interesting. So the sensors, it makes reference to the ambient temp. The gas cooler outlet temp is extremely important to it. We've got a pressure on the gas cooler outlet. And then as far as devices, it's just the stepper valve itself. It's the high pressure valve. So what I said is kind of interesting is the set points. You just give it a minimum gas cooler pressure and you define a maximum. So think of that as like wintertime, low ambient. I don't want it to get below some certain amount. So let's say our flash tank, we've set it at 520. We don't want the head pressure getting anywhere near that. So we'll set that at like 650, 700 pounds for our minimum. And then we set a maximum for a 110 degree day. We don't want it to get above 1,450 pounds before we relieve pressure to gain control of the gas cooler. But if you'll notice, we didn't tell it where it should be at. And some people call this the magic valve. That's why they call it that, because there's no defined set point, just a minimum and a maximum. And the reason for that is this COP line here. So there's a line on this chart here. What the valve actually cares about, this valve cares about where the gas cooler outlet temperature is in relation to this line here. What that line is actually, I think I've got it coming up on the next slide. My apologies. I got ahead of myself. So the valve is going to open and close to keep this sensor on this COP line here. So let's assume that my laser pen, let's assume that I were over here with the actual sensor reading. It was over here. The high pressure valve will lower the pressure to bring it back onto that line. And believe it or not, I could be over here and it will close a little to build pressure to bring it back up to that line. And the reason for that, so wherever it needs to be, whatever the pressure needs to change to get the gas cooler outlet temp back to the optimal COP line, that corresponding pressure is the setting. All that happens under the hood. It doesn't tell you anywhere what it's thinking. It's doing this hundreds of times per minute. So it is kind of magic. You just give a bottom range, top range. So I mentioned COP. You'll hear this thrown around a lot when people talk about CO2. It stands for coefficient of performance. And we're going to spend the next hour going through this formula step by step until everyone is memorized. I'm kidding. The simple version of COP, it means work over energy input into the system. So for us, Q equals the amount of heat removed. Like we put energy into the system. The work we're accomplishing is we're taking heat out of our display case, rejecting it into the ambient air. And to do that, we have to put in a certain amount of wattage. So short definition of COP, heat removed divided by the power input into the system. So I mentioned earlier the optimal COP line. So at this point, I did an exercise several months ago. There's a formula about a mile long and take you all week to do it if you're a newbie to it like myself, that basically tells you for a given conditions, a given displacement of a compressor, how much energy does it take to compress that low temp, to compress the low temp suction gas, raise it up to gas cooler pressure at a given condition. So that calculation there, the pack controller is performing that calculation on an ongoing basis. So it knows the displacement of all the compressors. It knows how many compressors are active. It knows the ambient temperature. It knows the pressure leaving the gas cooler. And it works to keep the temperature exiting the gas cooler on this line because it knows as long as that is happening, that we're using just the amount of energy necessary to do this work. And that's all you want. There's really not a way to use less per se, but we want to use just the energy required. So the high pressure valve, while it does serve the purpose of giving us liquid and warm ambience, it really cares most about energy usage by your compressors and maintaining specific conditions in the gas cooler. And then on the control, the last one on the control, the fourth area that we highlighted is the receiver bypass valve. And it's very simple. It's looking at the pressure in the top of the receiver, and then it's using the receiver valve to open and close. So basically, as the pressure rises in the flash tank or the receiver, this valve opens to relieve some of it. As the pressure drops, it closes off to back some of the pressure up to raise it back up. Having said that, the key set points, You tell it what set point you want. We use 560 or 520 for our example. And then you give it a minimum and a maximum. One difference between the receiver valve and the high pressure valve is the high pressure valve will never be fully closed or fully open. If you fully closed it, you're going to pretty quickly, that's a dead stop. You're going to pretty quickly trip the high side of the system on high pressure. If you fully open it, you're going to trip your low temp compressors, because at that point they would be the condenser, because you're just sending all the flow, especially on a hot day. This valve, however, will close completely if it needs to build pressure in the flash tank, and it will open to 100% if it needs to relieve pressure from the flash tank. So it references the receiver pressure transducer and just does its thing. Troubleshooting wise, these are the two new parts of the system: the high pressure valve, the receiver bypass valve. And typically they're not the issue. Most people would think they are because they're not familiar with them. That must be the problem. But the high pressure valve, if it's a warm ambient and you're towards an open position, it's working. If it's a cold ambient, it's towards a closed position, it's working. The receiver valve here, if it's maintaining flash tank pressure plus or minus 5 to 10 pounds, it's doing what it's supposed to. So just a quick recap on the control, and we'll take some questions. Suction group, we're using neutral zone plus and minus control to control the compressors. We're ramping gas cooler fans to maintain a delta between these two sensors. High pressure valve references ambient and a lot of other things, but it's basically trying to keep the gas cooler outlet temperature on the optimal COP line, again, which is coefficient of performance. Higher the COP, the more efficient the compressor. And then the receiver valve open and closes to maintain receiver pressure.